Today's Daily Dose of Math is about the power of sine law. This video assumes that you already know how to use the Soh formula, SOH, the first of the three basic trig formulas that are used to find unknown sides and angles in a right triangle. And this video assumes that you have heard of sine law and used sine law, another formula that's usually used for triangles that do not have a right angle, but that can still be used to solve for unknown sides and angles with cross multiplication. Here I have three examples of use of the SOH formula. All three different ways it can be used. In the first example, the unknown is the opposite side from the angle I'm using. In the second, the hypotenuse is in the unknown. And in the third, it's the angle itself that's the unknown. What I want to show is, although this formula is quite easy to apply, any of these questions could also be solved using sine law. And one important fact to know is that when you're using this formula, normally you never do the sine of the 90-degree angle. But in sine law, it's fine to do the sine of a 90-degree angle. So I'm going to apply sine law to this example. X over sine of 35 degrees has to be equal to 10 over sine of 90 degrees. Therefore, I'm going to do a bit of quick algebra and isolate my unknown. X is equal to 10 times the sine of 35 over the sine of 90. I should be able to solve for x by simplifying this. 10 times the sine of 35 equals, and then divide the answer by the sine of 90, and my answer is 5.7. Well, I knew that would happen. I already knew the answer because I successfully found it with the SOH formula. So what turns out to happen is that sine law is just as good for solving this question as the SOH formula is. Let's see if the same thing happens when we do the other two examples. In the second example here, x over sine of 90 must be equal to 8 over the sine of 31. Isolating my x, 8 times the sine of 90 divided by the sine of 31 will give me my answer. And the answer is 15.5, as I knew it would be. No unit of measure was given, so I'll use units as my unit. Now let's do the third example. This time we have an unknown angle. 12 over sine of 90 is equal to 5 over sine of the unknown angle theta. Isolating my unknown, sine theta is going to be equal to 5 times the sine of 90 over 12. So I'll simplify this. 5 times the sine of 90 equals, divided by 12, equals 0.4166, rounding to 0.4167, and then I do second sine to the answer, and I get 24.6 degrees. Of course, the answer I knew I would get. And this time I do have a unit of measure, which is the degree. So what we have shown here is that sine law can be used to solve any question where you would normally use the SOH formula. I wonder if that's true for the CAH formula. Let's find out. Okay, now we have three triangles set up that can be solved with the CAH formula. I'll solve these really fast with that formula. Okay, so using the CAH formula, I found that the side adjacent to the 33-degree angle here has to be equal to 15.1 units in length. This hypotenuse has to be 5.3 units in length, and this unknown angle is 38.6 degrees. Let's see if we can use sine law to solve these three problems. I have an extra step I have to do, which is subtracting from 180. 180 degrees, the total of the three angles in the triangle, minus 90 minus 33 is equal to 57 degrees. Now that I know the 57-degree angle that goes here, I can apply sine law. X over sine of 57 degrees has to be equal to 18 over the sine of 90. X therefore is equal to 18 times sine of 57 over sine of 90, and I'll simplify and I'll get my answer. 18 times sine 57 equals, divided by sine of 90 equals 15.1. Same answer. It is still working for the CAH formula. Now notice how when I did the Soh formula and then did it again with the sine law, I was using the sine key and the sine key. Now I'm doing the CAH formula, which I use the cos key in the calculator, but I'm still using the sine key when I solve it with sine law. Let's do the other two examples. (180 minus 90 minus 20 is equal to 70 degrees. Applying sine law, 5 over sine 70 must be equal to x over sine 90. X is going to be equal to 5 times sine 90 divided by sine 70, and x is equal to 5 times sine of 90. And of course sine of 90 is 1, so I'm doing 5 times 1. But I can just do it the way I wrote it. Divided by sine of 70 equals 5.3. Yep, same answer. Units. Now to get into the third example here, I can't subtract from 180. Because my unknown is the angle. So I can't use the same trick I did here. I still want to prove that I can solve this with sine law and avoid using the CAH formula. So what I'm going to do is Pythagoras' theorem. My unknown side is going to be equal to the square root of 32 squared minus 25 squared. So I'm doing a very quick shortcut into my Pythagoras theorem. But I can do this, and A is going to be equal to (19.9), well really 20.0. If I'm rounding to the nearest tenth, as I've been doing all along, it's 20.0. So now that I know this side is 20, yes, I can do sine law after all. 32 over sine of 90 has to be equal to 20 over the sine of the unknown angle. Sine of the unknown angle theta is equal to 20 times sine of 90 divided by 32. .625, and then second sine 38.6 degrees, which I knew would happen. So I have, with a little bit of extra trouble, still succeeded in showing that each of these three CAH questions can be solved with sine law instead. But I have to admit, in each case I had to do another step first. Subtracting from 180 is a really quick little step. Pythagoras not quite so quick. I wonder if I can do the Toa formula questions with sine law. Let's find out. Okay, so now I've set up three triangles that we would solve with the Toa formula. And I have solved all three using that formula. Tan of 34 is equal to opposite x over adjacent 11. X ends up being 7.4 units. Tan of 19 is equal to opposite 8 over adjacent x. The x ends up being 23.2 units. Tan of unknown angle theta is equal to opposite 5 over adjacent 10. The angle ends up being 26.6 degrees. What will happen if we want to use sine law to solve these? Well, this will sound a little familiar, I think. For the first one, we can do it, but first we have to subtract from 180. 180 minus 90 minus 34 equals 56 degrees. Then, knowing that this is 56 degrees, 11 over sine 56 is equal to x over sine 34. Notice though, I'm not going the sine of 90. I'm not using the hypotenuse or the 90-degree angle, but I'm still using sine law. X is equal to 11 times sine of 34 over sine of 56. And again, notice, I'm still using sine here. To avoid using the Toa formula, which uses the tan key, I'm using sine law, but of course I'm using the sine key. 11 times sine of 34 equals, divided by sine of 56, is 7.4, as I knew it would be, units. Subtracting from 180 and the triangle over on the top right, 180 minus 90 minus 19 is equal to 71 degrees. Applying the 71 degree angle, I can use sine law. X over sine of 71 has to be equal to 8 over sine of 19. X is equal to 8 times sine of 71 divided by sine of 19. X is equal to 8 times sine of 71 equals, divided by sine of 19 equals 23.2 units. And for the third one, and again this will sound familiar, I cannot subtract from 180 because the unknown was an angle. So I have to do Pythagoras again, or something like that. In this case, h is going to be equal to the square root of 10 squared plus 5 squared. Again, doing a very fast romp through Pythagoras. I want to write the word Pythagoras, though, to justify, to explain what I'm doing here. H, therefore, is equal to the square root of 125 11.2, and now I can do my sine law, although I'm running out of space. This time I'm using the sine of 90. 11.2 over sine of 90 is equal to 5 over the sine of unknown angle theta. Sine theta is equal to 5 times the sine of 90, which of course is 5 times 1, divided by 11.2. So shortcut, 5 divided by 11.2, 0.4464. I'll do it here. Sine theta equals 0.4464. So second sine of previous answer, 26.5. Theta ends up being equal to 26.5 degrees. Now this is going to be a rounding issue because I rounded to get the 11.2. So if I had kept that number to 4 decimal places, like is usually my habit, then when I did this, I would have ended up with 26.6 degrees. So we have succeeded in our quest to prove that sine law can be used in place of SOH, CAH, and TOA formulas, no matter which type of problem you're doing with the SOH, CAH, and TOA formulas. But in the case of the CAH and TOA, you have extra steps to do, those extra steps being subtracting from 180 or Pythagoras. I want to make one more point. I have met a student who really liked sine law and used it for everything whenever that student could. And that student actually did quite well in the exam for the course. But when I have met students who didn't like sine law and tried to avoid it, those students had a tendency to not do well in the course. The truth is, you should be using all the tools in your toolbox. So don't avoid a formula you don't like, just learn how to use it. But being able to use lots of tools is illustrated here because of the way we subtracted from 180 and used Pythagoras when we needed to, and we were able to fight our way through the problem even though we solved it in a different way than usual. That's today's Daily Dose of Math. Please like, subscribe, and share.